In the last video, we covered all 3 liner roll outcomes and their probabilities. So today, we will continue by examining the remaining possibilities for a 4-liner. With 5 chances, there are now 1,024 possibilities to examine. Let's dive right into it. The first step is to determine all the possible outcomes for a 4-liner. This time, there are 6 different roll cases to consider. For example, when rolling 5 times into a substat, there are 4 different outcomes. Each outcome represents an artifact that rolled into one of the 4 substats 5 times. The next case would be rolling 4 times into a substat and once into another. There are 12 different outcomes, which can be listed as follows. While we can continue to determine the different outcomes by hand, factorials can be used to verify the number of outcomes for each case. What we can do is start with the total number of substat slots factorial, which is 24. This is then divided by the number of recurring digits factorial. So, for the third case, there are 2 zeros, 1 2, and 1 3. This will give us 12 different outcomes. In fact, if we do this for the remaining cases, almost all of them will have 12 different outcomes. The next step is to calculate the probability for each outcome. This essentially comes down to determining the number of different arrangements that can achieve the same outcome. For example, when given 5 chances to roll upgrades, there is only one way to roll all 5 times into crit rate. This probability would be 0.098%, which is also the case if the artifact rolled into any of the other substats 5 times. Meanwhile, for an outcome with 1 roll of attack percent and 4 rolls of crit damage, there can be up to 5 different permutations. This gives us a probability of 0.49% for this outcome specifically. For later cases, the number of permutations can start to get out of hand, but fortunately, we can determine permutations more quickly using factorials. As we now have 5 chances to roll upgrades, our numerator will be 5 factorial to account for all possible arrangements. We can calculate the probability by taking 5 factorial and divide that by the number of rolls for each substat factorial. So, for the last case, the number of permutations would be 60, which will be the most common outcome at 5.86%. We can repeat this calculation for the different cases where the probability would be the number of permutations divided by 1,024. If we multiply the number of outcomes for each case with the number of permutations, we can verify that all 1,024 possibilities are accounted for. Finally, we can sort the first column, our presumed relevant stat, and sum the relevant cases to get our probability. Plotting this as a probability density function, we can see that there are 243 ways to roll no upgrade rolls, 405 ways for 1 upgrade roll, and so on. Comparing this to the 3-liner results we obtained, we can see that a 4-liner will likely receive more rolls into the relevant substat compared to a 3-liner. While the most common outcome is still 1, there is a small difference in the expected value for a 4-liner. We can find the expected value by multiplying the outcome by the probability of that outcome. This will give us 1.25 expected rolls for a 4-liner compared to only 1 expected roll for a 3-liner. We can also do a similar process for 2 relevant substats. We end up with a symmetrical distribution with 2 and 3 rolls being the most common outcome at 31.25%. Closely followed is 1 and 4 rolls at 15.6%, along with 0 and 5 rolls at 3.13%. Compared to a 3-liner, the expected value would be 2.5 instead of 2. We can also break down these probabilities further into the number of times each relevant substat was rolled. Starting off with 0 rolls, there are 6 different outcomes. Summing the probabilities will give us 3.13%. Next, for 1 roll, half the outcomes would result in 1 roll of crit rate, while the other half would result in 1 roll of crit damage. This gives us 7.81% for each result. For 2 rolls, there are 3 different results with 4 different outcomes each. The most common result would be 1 roll of crit rate and crit damage each. This is because there are more ways to roll this result. Crit rate could be rolled first followed by crit damage, or vice versa. We can continue to observe this symmetrical behavior for later results, where the tendency appears to lean towards an equal number of crit rate and damage rolls. Moving on, if we have 3 relevant substats, how many rolls can we expect? The answer is surprisingly simple. This is just the reverse case of 1 relevant substat. As we can see, the probability of that type of artifact rolling bad would be exceedingly slim, although it can still happen from time to time. With all artifact outcomes covered, what key concepts can we take away? The first thing is that having more relevant substats on an artifact will decrease your chances of it rolling badly. This is because rolling behavior dictates that you are more likely to roll a balance of all the substats as opposed to rolling solely into one substat. Second, having more chances to roll will increase your chances of rolling a better than average artifact. This does not mean that 3-liners are completely useless. In fact, there are many 3-liners out there that are very much usable. They just need to achieve high rolls. But that is a topic for another time.